Good evening, and thank you for making time to join us. Today, we're going to be continuing from where we left, and we finish off Clean's theorem once and for all. Okay. So the first thing that we're going to do is we're just going to look briefly at what we ended up doing here. So we ended up drawing this one for these two finite automata, and as a recap, we said that. Right, if we're going to be dealing with union, we're saying initial state of finite automata, initial state of L1 plus L2 is initial state for both L1 and L2, right? And then also same applies to final states. Right. So this was for union, and then for product, if we're dealing with product, we said initial state of L1 and L2, initial state of L1, L2 is the initial state for L1, initial state for L1, okay? Then final state is that of L2, okay? And then the L1, right? So we also say final state for L1 is equals to initial state for L2. State of states for L1 is equal to initial state for L2. Initial state for L2. So now these are the two that we did last. Now let's move on to another one where we look at the clean star. So if you look at the clean star, we've got the following. Right, if you look at the clean star now, we're saying, say we've got a finite automata with an initial and the final state, right? Whatever, say AB is a finite automata, right? To develop the finite automata for the clean star of this language, it's equivalent as taking null back to that. Right? So it is equivalent as taking null back there. But you know our finite automata cannot have null, so we need to find a way to deal with that. So now what this does is here final state is also equal to initial state. Final is also equal to initial state because of the path width with the null string, okay? And then next, so this is one. Number two, right, generate unique initial state. Unique, and I could rather add to say non-enterable initial state. All right. So we need to take a look at this and see how it does. So let's employ the usage of an example to demonstrate this. All right. If we've got R1, we'll find the clean closure of R1, right? So we're saying we need to have an initial state of Z1 that is equivalent to X1, okay? Right. So this X1, right, we want to have something like this. So we've got X1, and this is no longer in initial state. Right, so you go there with the now. So you want Z to be equivalent to this X1, and it's an initial state and also a final state, because when initial state is a final state, we say that when initial state is a final state, we say that now is accepted in in the word. So if you're in X1 and you encounter an A, you go to X2. If you are in X1 and you encounter B, you go to X2. So let's call Z2 equivalent to X2. Right? So this is X2. Now if you're in X2 and you encounter an A, right, you go to X1. But this X1, you want to label it differently. You are no longer going to this X1, you're now going to this X1. So X1 becomes Z3, define another one. Right? So Z3 goes to X1 as well. Now X2, if you encounter B, right? If you encounter B, you go to X3. X3, which is a final state and equivalent to initial state, which is equivalent to X1. So this is Z4. So Z4 is equals to X3, X1. Then if you're in X1 and you encounter, you go the X2, Z2, X2, Z2, nothing new here. Then if you're in Z4, X3 and you encounter an A, you go to X2. X1 and you encounter an A, you go to X2. So X2 is fine. So you go to Z2. If you're in X3 and you encounter B, stay in X3, X1. If you're in X1 and you encounter B, you go to X2. So this is Z5. So now we have Z5 equals to X1, X2, X3. If you're in X1 and you encounter an A, you go to X2. X2 and you encounter an A, you go to X1. X3 and you encounter an A, you go to X2. So this is X1, X3. Initial and final state are now the same. And then X3 and you encounter an A, you go to X2. So you're staying in Z5. And then if you're in X1 and you encounter B, you go to X2. X2 and you encounter B, you go to X3, X1. And if you are in X3, X1, if you are in X3 and you encounter B, you are staying in X3. So this is equivalent to Z5. So we cannot generate any more new states. So now we have identified the initial state here. Now we need to identify the final state. Anything with X3 in it becomes a final state. So this is a final state and this is a final state. Right, now let's draw the finite automata for this. We've got an initial state with Z1. With an A, you go to Z2. With a B, you go to Z2. Z2, with an A, you go to Z3. You go to Z3. With the B, you go to Z4. And then Z3 with an A goes to Z2. With the B goes to Z2 as well. Then Z4 with an A, it goes to Z2. With the B, it goes to Z5. Z5 with an A or B, it stays there. Right. So with an A here, Z5, X1, with an A, it goes to X2. X2 with an A, it comes to X1. Right. Then X, it comes back to X1. And then X3 with an A, it comes back to X2. Right. So let me just confirm if I'm missing something here. So I think we need to have this X3, X1 like that. Right. And then when we sit there, this will have to be defined as a new one, Z6. So Z6, so Z6, X2, X1. Then X1 you encounter B, you go to X2, X2 you encounter B, you go to X3, X3 you encounter B steady, so that's fine. And Z6, X2 and you encounter an A, you go to X1, x1 engine count and A, you go to x2, we stay in Z6. And then if you are in x2 engine counted B, you go to x3, x1. If you're in x1 engine counted B, you go to x2, so you go to Z5. So this is more like it, right? So Z5, if you encounter a B, you stay in Z5. If you encounter an A, you go to Z6. And if you encounter B, you go back to Z5. Right. So now, when I have this now, I need to label the final states. So all these two are final states on the Z5 and Z4. So these are the only final states, and this one is also a final state as well. Like that. So this is what the machine would look like. All right, let's move on to the other one and see. Similar but different. So here we need a unique non-interable state. So Z1 is equals to X1. X1 with an A, you go to X2, which is Z2. Right? X1 with a B, you stay in X1, which is Z3. Right? So X1. So X2 with an A goes to X3, X1. So this is Z4. Z4 is equals to X3, X1. And then X2 with a B, you go to X1, which is equals to Z3. X1, you go to X2, Z2, and you stay in X1, which is equivalent to Z3. Then X3 with an A, you stay there. X3, X1. X1 with an A, you go to X2, which is a Z5. X1, X2, X3. Then X3 engine counted B, you stay there. X3, X1. X1 engine counted B, you stay there in X1. So that's fine. X3, X1, you already have it as Z4. X1 engine content A, go to X2. X2 engine content A, go to X3, X1. So this is going to be go to Z5. And then X1 engine content B, stay in X1. X2 in content B, go back to X1. X3 in content A of B, stay in X3, X1. So this is equivalent to saying Z4. So now we can no longer do this anymore. We can come and draw the finite automata for that. Identify the initial state. This is the initial state, and also a final state. The final state, anything with X3, final state and final state. So as you draw the finite automata, we're going to have initial with an A, you go to Z2, Z1, with a B, you go to Z3. X2 with an A, you go to Z4. With a B, you go to Z3. Z3 with an A, you go to Z2. With a B, you go to Z3. Z4 with an A, you go to Z5. With a B, you stay in. So there was a mix-up here. This is supposed to be going over here. So with a B, you stay in over there. Then Z5 with an A, you stay in Z5. With a B, you go back to Z4. Only these two are now final states. So that's the end of Kleen's theorem. So that is the end of Kleen's theorem. We now need to move on to further chapters. So we're going to look at we have to look at we just need to now look at decidability, pumping lemma, and in properties of context-free languages. So we're going to be doing that over the next 2 lessons. So that will be Wednesday and next week, Monday. Right. So thank you very much for attending. Enjoy the rest of your day and meet again on Wednesday. Good night.